Hello and welcome to Tech Simplified TV. We are back with another technical topic. Clock is a significant component in digital circuit, and VLSI design flow is incomplete without clock tree optimization, clock tree synthesis, clock signal routing, and even selective usage-based power-saving method like clock gating. We have already published episodes on clock tree synthesis and clock gating. In today's episode, we will talk about some other aspects of clock like clock signal generation, clock non-idealities, and different types of clock network, their merits and demerits. If you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, clock tree and clock tree synthesis. Next, clock network. There are another slide on the very same topic, that is clock network. After that, challenges of clock network. Here also 2 slides on that topic. Then clock skew, jitter, latency and slew. Next, clock parameter and their impact. After that, conventional clock tree distribution. Next, clock mesh, H-tree and fishbone, multi-source clock tree system. And finally, there is another slide on multi-source clock tree system. So these are the pointers we will cover in today's episode. So now let's move to the first slide. Clock tree and clock tree synthesis. We already have an episode on clock tree synthesis. In our recent episode on power management series, we have discussed a little bit about clock tree synthesis, clock tree optimization, clock gating as a part of power management in an IC. Now here we will concentrate our discussion on clock tree and different aspect of it. This is a diagram of a clock tree. Both are diagram of clock trees. This one, the left one, represent before CTS, and this one represent the scenario of clock tree after CTS, that is clock tree synthesis. So first, let's try to understand what a clock tree is. A clock tree is a clock distribution network within a system or circuit. Clock tree includes the clocking circuitry and device from clock source to destination. Clock tree is a very important and integrated part of a circuit or chip. So a sequential circuit works as a sequential because of clock. In a circuit or a design, clock signal must be present in each and every sequential leaf level component or flip-flop. Therefore, clock signal has to travel a longer path, and we already have discussed that in power management series. Clock signal travels a longer path and consume a lot of power. So that is very important from aspect of power management. Here we will discuss about clock tree, its structure, its parameter, its challenges, about all of these things. Complexity of a clock tree and its number of clocking components used depends on the circuit and in its functionality. A clock tree, how much complicated it should be, depends on the number of components present in the circuit, and number of components in the circuit, sequential component in the circuit, depends on the complexity of the function it is performing. If the function is really complicated, a lot of work a design is doing, then its circuitry is complex and the clock tree and its components and its complexity is also higher in such cases. Now, systems can have multiple ICs with different clock requirement. In a system, there could be multiple ICs which has different clock requirement. A clock tree refers to the various clocks feeding to those ICs. Usually, a single reference clock is cascaded and synthesized into multiple different output clocks. This is the basic mechanism. First, a reference clock is usually there, a single reference clock, and multiple output clock is synthesized from there. We will see it later. Because this is the scenario before clock tree synthesis. Clock root, and this is the source, this is a destination. Clock root is the source and destination is a leaf level flip-flop. And before synthesis, it's directly connected. And after synthesis, that connection has been cascaded through some buffers. This level of buffers that gets included in CTS. This is the contribution of CTS. Now, clock tree synthesis is the process to distribute clock to each sequential element of the circuit. CTS is part of physical design in back-end flow. This is the total flow, and here the back-end portion CTS is done. RTL design is verified and synthesized into a technology-mapped gate-level netlist. RTL coding, verification, so it's starting from design specification, then RTL coding is done, then verification is done, on that synthesis is done, and we get a technology-mapped gate-level netlist. Now after that DFT is done, floor planning, and after that it's going in back-end. So floor planning, power planning and routing, global placement, detailed placement, these are all done. Now comes clock tree synthesis. So CTS comes after all these steps. Till now, ideal clock is used. Since all sequential elements are placed, real clock signal are included in CTS. So without CTS, clock signal goes to each end leaf cells or flip-flops directly from clock root. After CTS, there are a number of buffers inserted so that proper power management could be done. So this is the importance of clock tree synthesis that is done on clock tree. Now we will try to understand what are the parameters, how a network works, what are the different parts of this clock network, and etc. So we are done with this slide. We will move to the next slide. Clock network. This is the first slide on clock network. Clock network consists of a clock generator, clock elements are there, and clock wires. The clock can be generated by using ring oscillator or other non-stable circuit, but these are susceptible to PVT variations. PVT we know, process, voltage and temperature. These are the basic three reasons for variations. We have discussed about PVT variations. We have many episodes on PVT variations and variability. In episode of variability also, we have discussed in very detail about variations and its impact on device performance. Clock is important for a chip. Also, that clock can be generated on chip or off chip. There are two types of generation. Off chip clock generation is done using crystal and oscillator circuit, and on chip clock generation is done using PLL or DL. Now, routing a single clock around the chip is difficult issue. Another issue, if we use multiple clock, so if we use single clock, routing that signal across the chip with billions of gates is a tough work. It's a difficult issue. Another difficult issue, if we go for multiple clocks, then those clocks, their synchronicity is a thing. Clock signal might come at different times. So that delay between them is a tough thing to handle or control. Now, depending on applications, there are many timing components. Most common timing components are crystal oscillator, clock generator, voltage control oscillator. So this is a crystal. It's used to generate a single frequency. Crystal uses a piece of quartz which is cut at a particular angle and mounted on protective metal casing. It provides a frequency output when an electrical signal is applied. Piece of quartz which is cut at a particular angle and mounted on a protective metal casing. It provides a frequency output when an electrical signal is applied. Now, crystal oscillator. Crystal oscillators integrate the crystal with oscillator circuit, enabling the oscillator to provide higher frequency output. Now, clock generator. Clock generators are integrated circuits that generate multiple output frequencies from a single input frequency, which is a reference frequency. Crystal generate a single frequency. Crystal oscillator integrate the crystal with oscillator circuit. Clock generator these are integrated circuits that generate multiple output frequencies from a single reference frequency. And then comes voltage controlled oscillators, a self-contained oscillator that varies its output frequency in concert with different voltages from a voltage reference. So these are 4 parts. More parts are there. We will move to the next slide. More 2 components are clock buffers and jitter annuator. Buffers are basically ICs for distributing multiple copies of a clock to multiple ICs with the same frequency requirement. And jitter annuator or jitter cleansers are clock generators with specialized circuitry for reducing jitter. Jitter is, in one sense, we can call it's a parameter. At the same time, it's basically a non-ideality. That's uncertainty of a clock signal. So we will see it in later slides. And we have already discussed in a delay episode. In this episode, in coming slides, we'll talk about jitter. Now, off-chip clock has limitations. So, these clock buffers and jitter annuators. Off-chip clock has limitations like frequency is limited, multiplier is required. and uncontrolled clock phase. Synchronization issue is there. Now, PLL, which is an on-chip that can multiply the clock frequency. If clock multiplication is not required, DLL or DLL loop is used. So, this diagram is crystal oscillator it's going to chip 1, PLL digital system. Now, there is another chip. The main frequency is coming from this crystal oscillator and that is fed to one chip, that is to another chip. The way we have said. Now, PLL, these two diagram, one is for PLL, this is of DLL. So, PLL uses an oscillator that creates a new clock, whereas the DLL uses a variable delay line that delays the input clock. A phase detector produces a signal proportional to the phase difference between the input and output clock. This is a phase detector, loop filter and VCO, and there is a feedback path. Programmable divider. In DLL, there is a low pass filter and a delay line. So, a phase detector produces a signal proportional to the phase difference between input and output clock. A loop filter converts the phase error into a control signal. A voltage-controlled oscillator creates a new clock signal based on the error signal. This is about PLL. Now, in a DLL, same principle, but instead of changing the frequency, it just delays the clock until the phase is equal. That is delay lock loop. This is all about off-chip and on-chip clock generation. So, we are done with this slide. We will move to the next slide. Challenges of clock network. This is the first slide on the topic. This is the diagram. If you remember, we have already referred to this diagram in variability episode. What are the challenges of clock network? First is process variation. Variability due to device structure and other parameters lead to wafer variation. Due to this process variability and variations we are talking about in this slide, I have included this diagram. As we know that IC or chip or devices, they are manufactured in batches. And even we try our hardest, no two batches or no two wafers, or even, matter of fact, no two die within same wafer are absolutely identical to each other. There is some variation in dose, in energy and temperature during a process. As a result, the doping or oxide thickness, these parameters which are dependent on temperature, operating temperature, dose or energy, this gets a little bit varied. Even in a chip, one transistor from this side corner to another transistor to that corner are absolutely not identical to each other. So their performance are little bit varied. That is variation. Variability due to device structure and other parameters lead to wafer-to-wafer variations. The direct impact of process variations is on the yield and the performance of the design. The variations in the standard cell result in the mismatch across the various clock trees in the clock network. Due to variability, these parameters lead to wafer-to-wafer variation. From one wafer to wafer, there is variation in performance. The direct impact of process variation is on the yield and performance of the design. The variations in the standard cell result in mismatch across the various clock trees in clock net. Now, power supply variation. Supply voltage scaling causes variation in switching activity across the die. The uneven power dissipation across the die is the result of fluctuation in demand of current over a short interval of time. Ripples or noise voltage is induced in the supply lines due to presence of parasitic inductance. Parasitic inductance is there. For state-of-art chips, obviously that's there. We have already discussed about on-chip inductance in interconnect series. The current flows in the chip via interconnect, which has a finite resistance, and this resistance of the material that has a deep impact on the performance. So the variation in the resistance lead to IR drop. Clock is also a signal. Whatever we draw in our digital clock as this is basically a signal, 1-0 sequence, and the signal means voltage level. Current is flowing through the wires. This is the practical impact. Now, temperature variations. Temperature varies continuously on the chip while it's operating due to the power dissipation on the chip. Power dissipation is there. Obviously, junction temperature will increase. With the increase in temperature, the drain current decreases. Both device and interconnect depend on temperature and hence are affected by the variations in the temperature. How temperature can impact, we have discussed it in reliability episode. We have discussed it there. So now let's move to the other challenges of clock network. Signal integrity issue, timing violations, and design complexity. We have included this diagram because we are talking about signal integrity issues. Signal integrity issues include crosstalk, EM, IR. Crosstalk means interaction of when two parallel conductor lines or interconnects, they are running parallel, and in between it's not a free space, it's a dielectric layer. So it's working as a capacitor. That thing is crosstalk. The relative switching of wires on account of capacitive coupling results in crosstalk noise. With increase in the clock frequency rates, the capacitive coupling dominates and results in significant delay in data paths. If wire resistance is very high or the current through the transistor is higher than estimated, there is an unwanted voltage drop. This unpredicted drop causing time degradation in the signal and clock nets. It produces unwanted clock skew in the design and hampers the signal integrity of the design. We need to save the clock network from the signal integrity issue. Now, timing violations. A design consists of millions of gates and multiple clocks. Timing violations due to setup and hold, clock skew, and due to signal integrity issue cause hindrance towards the timing closure for a design. There are multiple things. Of gates, very long path for signal to traverse, signal integrity issue, setup, hold, clock skew. These all types of timing violations may happen, and we have to take care. So these are the biggest challenge for a proper timing closure of a design. Now, design complexity. Modern designs have millions of cells and the single chip is broken down into hierarchy of modules. The timing budgets are created for whole design, which permits the engineers to use hierarchical design methodology and work on their module for timing closure. Multi-stage clock gating structures are helpful for CTS. Multi-mode and multi-corner scenarios increase with the technology proceeding towards few nanometers. Therefore, timing closure as well as clock network have become challenge to the SoC designer. A huge number of gates there. Timing closure we have already talked. Another is multi-stage clock gating structures are there. We have already discussed about multi-stage clock gating in our clock gating episode. So many types of things are happening in a same chip while it's working. That is becoming very challenging thing. SoC designer need to keep all these things in mind. So this is clock source. This diagram is basically showing the latency. So if this is the scenario of a clock source to simple two flip-flop situation, just think what it can create when there are millions of gates, millions of flip-flop. How complex that structure, how complex that interconnect network can be. And this complexity is increasing because the application we want at consumer level, the application we want, that is becoming more complex. And again, nowadays, these mobile devices has become so popular, they rely on battery life. So again, we have to think about power management. There is a constraint on how much power you can spend. So this making the things more challenging. We are done with this slide. We'll move to the next slide. Now clock parameters. Here we'll talk about 4 parameters. Later we will see these are basically non-idealities also. We can call them non-idealities. Clock skew, jitter, latency and slew. The first, clock skew. We have already discussed about clock skew in delay episode. Clock skew is defined as the difference of insertion delays of two clocks belonging to the same clock domain. There are two flip-flop, same clock domain. So when clock is coming from clock source, there is a difference because we can see it's a very simple representation. Also, it will work. Like if clock source is this side, we can easily see that this path is shorter, this is moderate and this is the longest. Clock signal, it will be delayed to reach here and here compared to this flip-flop. If that is the clock, so at flip-flop 1, there will be delayed, this much delay. At 2, delay is there. That is clock skew. There are two types of skew, local or global, and value could be positive or negative. Local skew is the difference of insertion delays of two communicating flops of same clock domain. In a same clock domain, there are two flip-flops which two are communicating, and there is a difference of insertion delay or when it will reach those two flops. So that is local skew. And now global skew is the difference between the delay times for earliest clock reaching flip-flop and latest clock reaching flip-flop for same clock domain. That is the global skew. Now if capture flop receives the clock signal late than launch flop, then it results in positive skew. And similarly, if the launch flop receives the clock signal late than the capture flop, then it results in negative skew. They are communicating, and for signal transmission or data transmission, clock is required in two cases. Suppose data is going from here to there and clock is first coming here and going there next. So that is basically positive. skew, and capture the launch flop receiving the clock later, that is negative skew. That is all about skew. Now we will see what jitter, latency and slew. Now jitter, latency and slew. So clock jitter is defined as the deviation of a clock edge from its ideal position in time. We are expecting which time, that is the clock signal. This rising edge and falling edge, that may vary with respect to time, its position. So if that is ideal clock with jitter will behave like that if we plot them against time. Now clock jitter is uncertainty in the clock edge. The cause may be noise, a fluctuating power source or interference from nearby circuits. There could be many things. Noise might be there, power source might fluctuating. Interference from nearby circuit can also happen into such situation. Jitter can occur in both direction, positive or negative. Can be modeled by adding uncertainty regions around the rising and falling edges of the clock waveform. Clock jitter can be cycle to cycle, period or long-term jitter. Clock latency or clock insertion delay, defined as amount of time taken by the clock signal in traveling from its source to sinks. That is clock latency. This is the clock source, this is the clock divider, and it's so clock source to clock divider, that's source latency. And now from clock divider, it's distributed in the network. So that is from the end flip-flop, that latency, the time taken, that is network latency. Clock latency is source latency plus network latency. Now clock source latency is defined as the time taken by the clock signal to reach the clock definition point from clock source. That is the definition point and that's the source. Time taken by the clock signal to travel from clock source to clock divider is clock source latency, and clock network latency or network insertion latency, that is defined as the time taken by the clock signal in traversing from clock definition point to the sinks of the clock. So this is the network latency. So altogether total latency is source latency plus network latency. And another point is slew. Whenever we draw a signal, clock signal, it's like this. Sharp rise, sharp fall. In actual, it doesn't happen because even that rising takes some time. Ideally, we measure this clock cycle like this. In practically, we don't do that because the signal doesn't look like that. Slew is defined as the time taken to change the state of the signal from 0 to 1 or 1 to 0. So here it's 0, here it's 1. That's not instantaneous. A certain time is taken here, that is slew. Here also 0 to 1, that is output with respect to this input. Slew is defined as the time taken to change the state of the signal from 0 to 1 or 1 to 0. If switching is very fast, this rise is quite sharp and this time is less. And if switching is not that sharp, that will be like that and it will take more time like this. So we are done with this slide. We will move to the next slide. So clock parameter and their impact. Now every practical clock has parameters like skew, jitter, latency, slew, etc. which are also their non-idealities. That should not be. Ideally, we don't consider them. Actually, they are present there. Reasons behind skew and jitter: clock generation, manufacturing device variation in clock drivers, interconnect variations, number of buffers, device variation, wear length and variation, coupling, load. These all could be the reason. Interconnect variations. There are three basically reasons: clock generation, interconnect variation and environmental variation. Environmental variation is always there present because we are designing a chip to work in a practical situation where power supply might vary and temperature can vary. So clock generation, manufacturing changes could be manufacturing device variation in clock drivers, their number of buffers, device variation, wear length variation, coupling, load, interconnect variation. These are the reasons behind skew and jitter. Practical system to clock source, when we are manufacturing, there are differences. So obviously their performance will have differences. Now into network, interconnect variations are there. One clock is going, number of, depending on the buffers, how many device connected and their variations, and wear length variation, all things are taken in consideration. We have to consider all the things. Now, clock skew and jitter can limit the performance of a digital system. We know that. Obviously, designing a clock network that minimizes both is important. Now, how to control non-idealities? These are non-idealities. These are the impacts. Performance may degrade. So, how we can control them? Now, balanced path. H-tree network, matched RC trees can eliminate skew. What are these H-tree network, matched RC trees? These are how we design the path, the network of the clock, how they are connected to the devices. EDA tools can perform that. So HT network, match-start CPs are like that. Clock grids used in the final stage of clock distribution network that minimizes absolute delay, not relative delay. If paths are perfectly balanced, clock skew is 0. Distributed buffering reduces absolute delay and making clock getting easier, but is sensitive to variations in the buffer delay. Shielding clock wires to minimize or eliminate coupling with neighboring signal nets. Might be interference from neighboring signal net control or impact the clock signal, so we can shield them. Distributed buffering reduces absolute delay and makes clock getting easier. How buffers are distributed, that is also an key point. Now keep close an eye on temperature and supply rail variation and their effects on Q and jitter. So we have to consider that. Now power supply and noise limits the performance of clock network. So these are the points we need to check. We need to keep an eye on all of this. So we are done with this slide. Now we will see what are this clock network. Now clock network. There are 4 points on this section: conventional clock tree, clock mesh, H-tree and fishbone, and multi-source clock tree system. Now conventional clock tree distribution. Single point CTS is the choice for designs when frequency is lower and number of sinks are less. So it's a conventional CTS. This is clock source. Now these are the clock tree cells. This zone. After that, clock gets and buffers. And finally, these are the loads. So as name suggested, having single clock source which distribute clock to every corner of the design. This is the single clock source. In single point CTS, the point of divergence lie at the clock source. So it shared very large uncommon clock path, more susceptible to OCV variation. Common path is very less. Uncommon path is very large. And this process is more susceptible to OCV variation, on-chip variation. So what is OCV? We already have a episode on that. You can get to know in details. Watch that episode. Clock gates are strategically placed near source, saving large amount of dynamic power. What are the advantages of this distribution? Simple to implement, very simple structure, better clock gating, reducing power dissipation. And disadvantages? Higher insertion delay, more uncommon clock path, more prone to OCV, tough to achieve lower skew due to asymmetric distribution of sinks. Conventional CTS is not a good choice for high frequency signals having high number of sinks all over core region. Implementation is easier, although very prone to OCV. Quite good at reducing power dissipation, better clock gating, although there are some issue for also not good for high frequency signals, and it's really tough to achieve lower skew because of asymmetric distribution of sinks. So this is the conventional clock tree. We are done with this slide. Now we will move to clock mesh. So this is clock mesh, another type of clock network. Clock mesh is divided clock domains into many grid areas. Clock signals connect to the clock mesh node through pre-driver buffer chain. This is clock source, pre-mesh driver. Now mesh driver, this is before the pre-mesh distribution. This is a mesh net, and mesh these are the drivers for mesh, and clock gates and receivers are on the other side, and finally loads. The global mesh used 2 layers of metal wiring crossing each other in order to spread the clock signal that placed by top level chain to the whole clock domain and will control clock skew and clock delay. The distribution scheme is different from the conventional one. There is a network of pre-mesh drivers to drive the clock signal from clock port to input mesh driver. There is a clock network. This is source and these are mesh drivers. So there is a network in between that drives the clock signal from source to this mesh driver. The output of all mesh drivers will be shorted using metal mesh, which will carry the clock signal across the block using horizontal and vertical metal stripes. In mesh structure, power dissipation is high as clock gate cells are inserted after the mesh net, so clock gating is done at local level only. Advantages: lower skew, highly tolerant to on-chip variation, and possible to achieve lower insertion delay. Disadvantages: more power dissipation and difficult to implement. Structure is complex. It's more power hungry basically. So power dissipation is more. Dynamic power dissipation in this structure is more, although OCV on-chip variation is less and delay is less. So these are 2 structures. We are done with this slide. We will move to the next slide. Now H-tree and fishbone. The H-tree structure is highly symmetrical. The pre-drive buffers evenly distributed on the trunk, and it can manage clock skew for the clock domains with a large number of flip-flop. H3 structure consumes more routing resources while there will be more power consumption. So this is H3 structure, it's a symmetrical in structure, and this one is fishbone. In fishbone, this way, because of this structure, it's called fishbone. This is a fishbone structure, and there are more different structure, like this is tree, as we can see, this is X tree, this is H tree, like this, and tapered H tree. These are 4 different topologies. And now finally, multi-source clock tree system. MSCTS is a hybrid system containing the best aspects of a conventional clock tree and pure clock mesh. It's a hybrid system between conventional clock tree and a pure clock mesh. Now, clock mesh delivers the best possible clock frequency, skew, and OCB results, and whereas conventional clock tree delivers the lowest power consumption and the easiest flow. So, multi-source CTS offers a compromise between the 2 methods while favoring the OCB tolerant nature of pure clock mesh. A MSCTS design comprises of 3 different structures in the design act. One is pre-mesh clock tree, multi-source mesh fabric, and moderately sized clock tree. Now, what are the benefits? Better performance and lower skew than conventional CTS. That is clock tree. Now, better OCB tolerant than conventional clock tree, better multi-corner performance than conventional clock tree, less power consumption than pure clock mesh, and greater tolerance of irregular, highly macro density designs than pure clock mesh. Faster and easier flow than pure clock mesh. It's taking benefit of both the structure, conventional clock tree and clock mesh. Now, pre-mesh clock tree. We have seen there are 3 parts. So, first, pre-mesh clock tree. This is the clock route. Now, this is pre-mesh clock tree. And here, coarse mesh is there. And after that, multi-point drivers and subtree is there. So, each buffer in the pre-mesh tree drives 4 other buffers. That's pre-mesh topology similar to H-tree placement and routing. H-tree structure is uniform, scalable, predictable method to distribute root clock over a large area. Also tolerant to corner variation because of their balanced structure. So that's pre-mesh clock tree is like conventional clock tree. Now, multi-source mesh fabric. The multi-source mesh fabric resembles a power ground or clock mesh fabric, although less dense. The coarse fabric smoothes out any remaining clock arrival time differences from multiple H-tree buffers that directly drive the fabric. The mesh skew at the mesh plane is effectively 0. So, multi-source mesh fabric is there. Its resembles a power or ground or clock mesh fabric, also less dense, and coarse fabric smoothes out any remaining clock arrival time differences from multi-H-tree buffers that directly drive the fabric. And the measured skew at the mesh plane is effectively 0. And now finally, moderately sized clock trees. Multiple clock trees that are attached to the coarse mesh. There is a multiple clock tree that are attached to the coarse mesh. That structure gives the technology its name from multi-source clock tree system. It's a local network, multi-point drivers are there, integrated clock gating is getting done here, and this is the subtree. So that is multi-source clock tree system. After mesh, there is a subtree, so that name comes from this structure. We are done with this slide, and we are done with this today's episode that we had all about clock tree in VLSI. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any question, please put it as a comment. And if you have a dislike, also put it as a comment. Thank you again and bye for today.